Hello, everyone. Welcome to the first session of Coffee O'Clock of this year. I am Amaya Ambition. I'm a PhD student at Karlsruhe Institute of Technology in Germany. So today I'll be substituting for Akash and be your host today. So we will be continuing with one of our sessions from last year in November, where Kishor Part-2, a research scientist from Institute of High Performance Computing in Singapore, was talking to us about the challenges and opportunities in the noisy intermediate scale quantum era. We're so thankful for agreeing to do a second session with us, Kishor. The screen is all yours.
Thanks, Amia. I hope I'm pronouncing the name correctly. Thanks for the invitation, and I would prefer if participants keep their camera on so that I feel it more interactive. So let me screen share. Okay, so last time we talked about this. Basically, we talked part one. I would say mostly focused on part one about what are the challenges and opportunities in the NISQ era. And basically, mostly I focused on, I would say, what does it mean to find out whether a device is performing some quantum computation indeed or not. So it's a quite non-trivial problem, and basically we discussed this. There are three approaches to demonstrating quantumness. So one is basically implementing something like Shor's algorithm. So for example, you assume that factoring is hard classically. And under that assumption, if somebody can factor, then you basically, trust their claim that they indeed have a quantum computer. But these are, I would say, these are something which, which are quite in the future and cannot be, implemented currently. Then there are, those based on sampling tasks. So the circuit sampling approach, and these are basically, I would say, current term, but the issue is that it's difficult to scale them, and the verification is difficult, as you scale number of qubits. And the third one is basically the interactive proofs. So where you ask a question and you get an answer. And in this interactive, question answer setup, you try to check whether you can, test the quantumness. Yeah. And this is something where the verification is easy, but at the moment, implementation is a bit hard. I think maybe, instead of from my iPad, I might want to share it from the laptop because there's a small lag. I don't know why. So we talked about basically this proof of quantumness and then useful quantum advantage, which is why the NISQ algorithm is something that I will focus today. And there are many challenges, like one of the challenges, challenge of taming noise. Actually, here also I discussed last time that coming a bit, proof of quantumness, which can be implemented on currently available quantum devices, for which it's difficult to spoof. And so, there are three kinds of, protocols at the moment. And we require, we want a protocol which is, easy to implement, I would say, easy to verify, but hard to spoof. And at the moment, there is no such protocol. I mean, we have Shor's algorithm, which is easy to verify and hard to spoof under the assumption that factoring is hard, but then Shor's algorithm cannot be implemented on the current time devices. And we have sampling tasks, but the difficulty is that they're easy to implement with the current devices. And that's why, like we have these 3 different sampling based experiments have been performed, like Google experiment, there was one Janway group, and then there was one from Xanadu. But it's hard to, like verify, first of all, as you scale. And then in the presence of noise, we do not have a strong complexity theoretic argument to ensure that, like they are hard to spoof. So yeah, that is the issue. Yeah. So there is this paper by, like Doritaranov, Zerlan, Liu, and Wazirani, where they come up with a polynomial time classical algorithm for noisy random circuit sampling. So basically, in the presence of noise, many of the results that we had, basically the cross entropy benchmarking measure which has been used, it's no longer, I would say, a measure which can be, like trusted in the adversarial setup. So I also discussed about, like this third approach, this interactive proof, where you ask a question, you get an answer. And these are easy to verify and, like hard to spoof. But the issue is that, so they are, like interactive, like, you ask a question, you get an answer, and this kind of question and answer. But the issue is that number of qubits that we require, that's like, 10 to the power, I don't know, like 1,000 something. And the width can be, like as high as 10 to the power 5 or 6, 10 to the 6. So there was a paper where they managed to reduce the the depth from 10 to the 6 to 14, but the number of qubits that they required, like it went into billions. So we need, a protocol which can, I don't know, like can be implemented on, let's say, 1,000 depth circuit, but, like 1,000 width circuit, but, like also depth should be within 1,000. So like some kind of trade-off is required. So this is a very, I would say, one of the holy grails of near-term quantum computing, like coming up with an interactive proof protocol, or, like some protocols, like, which can be used to demonstrate quantumness, for which feasibility is easy, verifiability is easy, and soundness is hard. We do not have any protocol, like, at the moment. So this is a very important open question, and, like worth pursuing. Okay, so I discussed that. Then, like, the second part where, so first part was useless quantum advantage. Like, you want to basically just make sure that your device is doing something quantum, and whatever the device is, like performing, like there is no classical device that can, perform the same task with polynomial overhead. But that is something which will not pay the bills, right? I mean, you need to come up with some useful problem. And that's where, like many NISQ algorithms have been proposed. And they are in problems in simulation, optimization, quantum chemistry, machine learning. Simulation being quite famous because, like, we all know this famous quote by Feynman, which says that, yeah, like nature is quantum mechanical. So why not use quantum computer to, simulate it? And many applications have been proposed. So like, all this, I just put I would say, small, this screenshot from that paper. And actually you can see there are like many new papers being written and all. And I mean, as of now, we do not have any algorithm which can, I would say, I mean, first of all, demonstrating, like that we have done something useless, even useless, which cannot be implemented on a classical device. That itself is so hard that, like I would say, coming up with an algorithm, like which can probably, or let's say even for some use, heuristically give you advantage over their classical counterpart at the moment is an open problem. So even though so many algorithms, papers have been written, there are like many problems they suffer from. So, like there is famous algorithm called VQE. I mean, it's again a heuristic where, like it's similar to the variational principle of quantum mechanics. What it says that you prepare some wave function, you estimate the corresponding loss function, and you update your parameter, this theta using some gradient free or gradient based approach. This is all nice, but then the issue is that, how do you update the parameter? And that can be, quite complicated. Like it can be a non-convex optimization in general. And there can be many rounds in the sense that you update the parameter and then you go through the same process again and again. There is a sister algorithm of VQE called variational quantum simulator, where instead of finding the ground state of Hamiltonian, you try to simulate the dynamics. So you can think of like a VQE for the static case, VQS is for the dynamic case. And here also you calculate some certain objects on the quantum computer, you solve something on the classical computer. So in the VQE you basically solve an optimization problem on the classical computer, and then basically you update your answers and keep on going in this loop. So similar, approach you follow for the VQS also.
Kishor.
Yeah. Is there a question? Yeah,
this might be a very trivial question, but you mentioned the optimization need not be convex. So what does that exactly mean? So during that parameter update rule, that your state might go outside the set of states that your parameterization can hold, or could you tell me what convex?
No, so basically, So basically, the way it's parameterized, the states are parameterized, you will always have a valid quantum state. So that's not a problem. Mm-hmm. The issue is that, let's say if you have a convex landscape, like somewhere might be, discussing that, So normally if you have a convex landscape, you will have something like this. So like you start from here, you will, reach the solution, and that's the solution you want, like your local minima is global minima. But if let's say if you are in this kind of a thorny landscape, then depending on your initialization, you will land up into some local minima. And because Hilbert space is like, I would say, this space is quite huge, like lot of, I would say, this can lead to problem in your training. So people have shown that, training the classical part of the optimization of variational quantum algorithm is NP hard, even for the scenario which is, a perfectly classical simulable. And the origin of that can be traced to, like the presence of several local minima in the problem. So barren plateaus and all, which people talk about are like definitely one problem. But at the level of optimization, local minima, is another problem you can mention.
I see. So this, so the convexity of the landscape is how few local minimas are there. And does this have anything to do with
convexity basically means that, if your optimization program is convex, then there will be no local minima.
Okay.
Like there will be every local minima will be a global minima.
Okay.
So you will have, like this. And actually, if you think about the ground state problem, is actually, a convex problem. It's a convex optimization problem. But so this is what they are trying to solve. But the issue is that in the regular VQE approach, your row, you optimize your pure states, and set of pure states is not convex. On the other hand, if you optimize your density matrices, that's a convex set. So you can take, for example, two quantum state on the block sphere, take their convex combination, that will not be on block sphere.
Right.
So convex combination of two pure state will be maybe a mixed state, but if you are optimizing over pure state, you do not have that in your set. So basically, the idea is that you need to map your optimization, in a smaller dimensional space, such that convexity of the, problem is maintained. So this is what, we did, in one of our paper, and here, so regularly, you have training in whatever takes exponential time, like in general, but in our case, the training can be done in polynomial time.
That's really cool.
Yeah,
I actually just started following Waters' lectures, and there they were talking about convexity and stuff. That's why I asked. Thanks. Nice. Awesome. Yeah, please carry on.
And then, and then it is a VQS, and then there is also a linear system. So you want to solve AX equal to B. So, the question is that you have been given A and B, you need to find X. So an example could be something like, you have X1 plus X2 equal to 2, X1 plus 2, X2 equal to 3. So here A is basically 1, 1, 1, 2, B is 2, 3. The goal is to find x1, x2, which is, like equal to 1. So this is what, like you solve in your linear system problem. In quantum linear system problem, basically you are not solving the linear system problem. You look at the quantum version of that. So you are trying to find, like you have A ket x equal to ket B. And, like when you can't solve the problem, the approach that they follow is that they change the problem. And so the problem, like the quantum linear system problem is not exactly a linear system problem. Here you are interested in, like finding this ket x, and not necessarily like ket x, but some property of ket x. So like with respect to some observable m, you are interested in finding, like ket x, bra x, m, ket x. Yeah. So that's what you are interested in. So basically you need some way to prepare your B and some way to, like access to the matrix A. And yeah, I mean, you can actually, the key idea is that you can construct the problem as a Hamiltonian problem. And if you can, like find the ground state of this Hamiltonian, then you will end up finding, like solving for the linear system problem. So you can see that if you have Ax equal to B, then it implies that H of x equal to 0. And you can see that, like this matrix in the middle is actually a projector. So its eigenvalues are 0 or 1, and A is equal to A transpose. So, you see that, this is a PA matrix. So the smallest eigenvalue is basically, like 0. So, I mean, and you can see that, like if your X solves the linear system, then H acting on X, that will be 0 because, like if you put a X here, then Ax equal to B, and B is orthogonal to identity minus BB. So you have 0 here. So basically you find the ground state of this Hamiltonian and you are done. And yeah, like I mean,
why is there an A on the left, the first A?
Yeah, it's supposed to be A transpose, but like I mean, it's some like matrix that we construct from like A and B, and so because A is equal to A transpose, it does not matter. Yeah.
So I'm asking, why do we need A transpose? Because if you just remove, if it is just I minus projector B into A.
Yeah. But then how do you maintain that the H should also be symmetric, right?
Okay. Got it.
Yeah. Okay. Yeah, that's a good question. Yeah. So, and then like, many papers have been written, like whatever VQ is on. But the issue in many of these approaches is that, you need this classical quantum feedback loop. And so you perform some operation on quantum computer, it comes to classical computer, you update your parameter, it goes there, it waits in the queue. Sometime, like it's like waits there for, I don't know, like 1 day, and then, like you get down. And often, let's say, even if you have dedicated access, which people don't normally have, it takes this kind of loop. You do not know how many circuit evaluation you need to do. And there is, like this, you need to perform measurement corresponding to every, like time you are computing some object here. So in non-convex optimization, first of all, you do not have guarantee that how many loops you will have. Like it will go there, come back. And every time you have to perform those many measurements, which means you need to use quantum computer a lot many times. On the other hand, if you think about, like algorithms like, Shor algorithm or many of the algorithms that we have, we perform something on quantum computer, we get the data, we post-process it, and we get the answer. But here, this feedback loop can, like really kill I would say, the feasibility of overall process. And that's why, like, most of the VQ, let's say if you try to implement for 10 qubit or something, it can take you really days. On the other hand, our regular computer can do it, I don't know, maybe in seconds or at most minute, yeah. So also there is barren plateau problem, like you are interested in finding the ground state. Sorry, like the way you do training is by looking at the gradients, and often, like the gradient, can be 0, and not only that, the variance can decay exponentially in number of qubit, which means using, Chebyshev inequality, you can actually bound that for every instance, like, the gradient is very small. And this is a big problem. It has been studied, and like people have written several papers and all. Yeah. So I think in one of the papers we talked about, like this problem-induced barren plateau here with Patrick. Moreover, that even also this non-convexity issue, like which says that, training variational quantum algorithm is NP hard, and whatever, there are other challenges also related to critical points and so on. Just mentioning that, many challenges. So here we talk about, we proposed one approach, which says that the idea of many of these variational quantum algorithm is that you are in a big space. From big space, you go to a smaller space. But in the process of going from bigger to smaller space, often people, many of the algorithms that we have, you lose track of the convexity of the problem. On the other hand, here, we propose a mapping which, where you do not lose track of the convexity of the problem. So problem remains convex. On top of that, because it's convex, a training is in polynomial time. So this, criticism does not apply to our algorithm. On top of that, there is no quantum classical feedback loop required. So you calculate certain matrices, like D and EI on the quantum computer through sampling. And once you get that, you solve this semi-definite programming on the classical computer. And which is like, SDPs are polynomial time algorithm in input. So you do not have the classical quantum feedback loop. You do not have, I would say, training issue. But there can be other issues like, how do you find the right answers? And at the moment, I do not know any approach, which can give you approach, solve this problem systematically for any instance. And actually, this is a hard problem, in general, because finding the ground state of Hamiltonian, for example, is a QMA hard. So we do not expect quantum computer to, solve it in the worst case. But at least, more systematic studies are required, I would say, to, understand, this approach here. So that was about, NISQ algorithms, now let's talk, a bit about, taming noise. So we are talking about NISQ, so noise will be there because, noise is one of the, I would say, challenge. Noise is difficult, So people propose something called error mitigation, where the idea is that, you perform, you get more samples and you try to calculate, for example, a noiseless expectation value from noisy expectation value. So, but then there's this sampling cost, you need to take too many samples, and it helps actually. Like in the beginning, there was papers presented where they saw that, when you perform whatever, error mitigation, you see that, it very much matches whatever is, the actual classically simulated curve. So the green ones you see, they are at the spot where they should be, and similarly blue here. So very nice. But the issue is that, sure, you can, for 2 qubit, 5 qubit, whatever, you can do this, whatever this thing. And quantum error mitigation, people wrote all these reviews and all, where they talk about error mitigation. Many different approaches for error mitigation has been proposed. It's all good and nice, but there, and also for quantum error mitigation and, the relation between, fault tolerant quantum computation, they have been explored. So very nice paper. But the issue, as I mentioned, the issue is with respect to the sampling cost. So you need, exponentially many samples. And that is something, I would say, challenging. So coming up with a protocol which can, may require less samples, and can help solve the problem, can help tackle the noise in the NISQ era. You can obviously reduce the noise by, by improving the hardware, I would say. But from the theory side, coming up with a nice protocol, it does not cost much. That's basically, a very good open problem. And there were also this, nice paper by, Franca and Raul Garcia Patron, where they, make this statement that, the bonds we often indicated a substantial quantum advantage are unlikely for classical optimization unless noise rates are decreased by orders of magnitude or the topology of the problem matches that of the device. This is the case even if the number of available qubit increases substantially. So this was a very powerful result, and I mean and basically no matter where you want to, where you start with, basically noise basically takes you to the fixed point, the noise model, and currently available, so basically, I mean, these are some really challenging problems, and it would be nice to, find out whether we can, design more. Yeah, first of all, can we come up with protocols, which does not require much error mitigation, and then on top of that, can we come up with better techniques? I think maybe a mixture of error mitigation and error correction as we are reaching, entering in the intermediate scale regime and all, and see whether we can help solve the problem. So this is all I would say a quite nice direction to look at. Finally, yeah, I think compared to last time, this time I would say I'm going a bit fast because I think the background, I already said the last time. Yeah. So I think for viewers, who are finding it something fast, or maybe they can see the last video and continue. And finally about software. So the software is another, I would say, you see, right? I mean, back in 2016, when IBM put their quantum computer on the cloud, I think they had 5 qubits or something, when I started my PhD. And as of now, today, they have around, I don't know, more than 100 qubits, maybe 100 something, and was there 400 something, like some number, they just some number which is large. And yeah, and basically, at the same time, a lot of development is happening, people are trying to come with many things like SARC, Penny Lane, Pikeweed, and I think people are coming up with, more and more software. Also for quantum error correction, people are coming this STEAM package by Whitney, and yeah, many nice, many packages and all. Now the question is, I mean, many of them, there is a lot of redundancy here, many of the tasks, which one package does, the other also does, but I don't know whether one needs too many packages. Maybe one needs a package which runs fast, and and then at the same time it's quite versatile. Yeah, I mean, we do not need 1,000 different packages, I would say. And at the same time also, I mean, we need to see whether, there are problems for which we need, I would say, some software solution, but we don't have. And that's where I think maybe software people can also, contribute. There's certain external libraries again. Yeah, sorry.
From where are these tables?
Yeah, this is in my paper. Yeah, I mean my paper with other people. Yeah. So NISQ paper. Yeah. So there is external library, and I believe I think by today, I mean it's not the best representative because I think people are coming up with many. So, but you can find at least 90% by when we wrote it. I think this was the representative table, but the field is evolving fast. So I think it's at least captures still 90% or something of existing list. So these are, I would say, the references. If you want to look at these things in detail. And I think this concludes the talk. Yeah. So I mean, as I mentioned, there are these challenges at the software level, at the noise level, at the algorithm level, and also device, basically quantum device certification, or effectively proof of quantumness level. And something I would say which is quite close to my heart is coming a bit, I would say, an interactive protocol which can be implemented on the. So can you get rid of this and put here current? That's I would say. So step by step, if we get this done, then and we can think about some useful advantage. And yeah, so that's it. Thanks.
Thank you so much, Kishor. I guess there are no other questions from anyone.
Maybe.
Yeah.
No. Just so you mentioned the interactive proofs, right? Do you have any areas or places that you feel have potential? So what kind of interactive groups are interesting?
Yeah.
So that's one question. And maybe the next question is, let's say a bachelor student is interested in all this, right? A bachelor student who's watching this, and then let's say maybe they're third year and they're thinking like, what's a cool bachelor thesis to do? What advice would you give them, basically? Cool, thanks.
Yeah, I think like understanding. So like I think it depends. So one can depends like from what perspective, like what one wants to learn. So let's see if one wants to learn the nuances of proving, demonstrating quantumness, then interactive proofs is like I would say a beautiful direction. So I mean, so like it's basically it's a setup where like there is it's a classical verifier and a quantum prover, and the prover basically claims that they have some ability. So ability, like here basically they claim that the prover claims that they have a quantum computer, like, and they can perform a task which is classically not possible. Now, how do we check it? So we ask a question and the prover responds. Then we ask a question again and the prover responds. So it's like, this kind of the way one interrogates the criminals, like you ask them, they give an answer, you ask them, they give an answer, and basically you need to check the consistency in their answer. And if you find that something is like inconsistent, then you basically deduce that something is fishy there, and you do not buy their arguments. So their claim. So similar thing, it happens in this here. I think there is something which I mentioned last time also, is that one example could be, let's say, I mean, for example, like let's say Amya basically claims that like she can count the number of leaves in a tree. Now, so that's a, like that's a claim that she has. I mean, like, and maybe she can count number of leaves in the tree. Now, how can we like come up with a protocol where I don't have ability to count the number of leaves in the tree, but somehow I can like verify, or like I would say reject her hypothesis that like she can, or like she can count. So one of the approaches, like where you like, can somebody tell like what can be a simple protocol, like using which you can I mentioned it before. Yeah, I mean, it's basically I ask her, okay, I mean, I show her a random tree and I ask her how many leaves are in the tree. She says n. Then I go out and I like pluck maybe, I don't know, like 1,000 leaves or something, and I ask her like how many leaves are in the tree, and if she gives me answer as n minus 1,000, or like then I then I accept her hypothesis, otherwise I reject it. And I mean, this is a two-on protocol, and like you can apply to any tree, and you can like apply to tree of any size, and like I mean, you can always so this is, so you see that like normally if you do not give me this power of interaction, then I cannot basically, because Amya is powerful person, like she can count number of leaves in the tree. On the other hand, compared to her, I do not have abilities. So it's like it becomes there is this power difference, and that's what we have here on the quantum computer. And the classical quantum computer is a powerful device. Classical computer is not so powerful. But let's say if you ask the verifier to query and get an answer, and then depending on that you can solve more interesting class of problem. So interaction is very powerful. So no one could ask, like let's say the prover can say, like I can solve this machine learning problem faster than any quantum computer. Or you say that I can solve this Hamiltonian simulation problem faster than any classical computer. I can solve. So you can ask different questions. I mean, it's totally uncharted territory. So here we are asking, like I can do something which is quantum and no classical computer can do. But we could say, like I can I can factor factoring maybe might be not that. Yeah, so you can take any problem, so quantum finance problem, some I don't know, like machine learning problem, and you have a claim, and the prover has a claim, and like and when the verifier might want to like check that. So many interesting papers have been written, like can you do self-testing in this setup? Can you generate a randomness in this setup? Can you like verify entire quantum computation in this setup? Like, I mean, can you decrease the number of rounds? Can you, make it, can you decrease the number of qubits required for your implementation? Like, it's a very nice area, and I think it's something which is worth exploring. Yeah.
Awesome, thanks.
There was another question from Anuj on the chat. He asks, as noise is inherent feature of NISQ quantum computing, what will be the suitable application which can be benefited by this platform?
Yeah, so this is a very good question, and I mean, like, at the moment, we do not know any application. Let me stop the screen share so that I can also directly read the chat. And yeah, so basically I would say at the moment, yeah, it's a $1 million question basically. I mean, people are basically trying to find I would say, and some application area which you cannot, for which you can definitely get an advantage on the, if you perform it with the NISQ devices, and on the other hand, it's something which is, interactable, if you try to perform the same task on a classical device. Now, we do not have any hint at the moment, which problem might be. I mean, definitely there are certain candidates like, Hamiltonian simulation, maybe analog simulation might be, analog quantum simulation is something which can be, I would say, the first application. And I think, as many people say, maybe one of the first application of these devices would be, very academic. So just understanding physics or some chemistry problem, which may not have direct industrial application. And then slowly, I think they might transcend into something which is, industrially relevant.
Yeah, hi Kishor. Sorry for interrupting. So my question was specific to the noisiness, which is actually there in the quantum computing platform. So there are many other things, but there are certain things. So like something like using the negative feature of somebody or some object for the benefit. Okay, so I'm specifically my query is actually around the noisiness of the quantum computing can be benefited, some application can take benefit of that feature.
Yeah. No, I mean, that's a beautiful question. Yeah, I think I did not understand your first time. So noise can sometimes benefit. So let's say there are this paper where they where people have shown that, let's say you are training, and if you are stuck in some local minimum or saddle point, because of noise, fluctuation, you can leave, you can get out of the saddle point. So sometimes, noise can be useful. Now, one has to see that, how much noise is useful. I mean, this is a good question, because let's say if you add too much noise, then it will become classically simulable. And if your overall, a protocol is classically simulable, then there is no hope for quantum advantage there. On the other hand, you would like to have, noise, which, helps your protocol. So maybe, finding that sweet spot would be, quite important, where the problem remains classically difficult. At the same time, noise helps you, let's say, in training or something. Also, I think understanding the nature of noise that we have in the quantum case can be quite different what we have in the classical case. So understanding noise and its implication, just from theory perspective also, I think that's a very good research problem. And I think noise has not been understood in great rigor, when it comes to NISQ devices, because recently only there were quantum error correction and everything was discussed back in the past, but when it comes now, as people are trying to build these NISQ devices and scale them and all, and trying to come up with protocols, people are beginning to understand noise at a more fundamental level. So I think this is a very good direction for exploration. Yeah, but yeah, I mean, one has to really find that sweet spot where you can get benefit from noise. Yeah.
Thank you, Kishor. So I think Rishi is written something.
Yeah, no, I remember reading a report where they were saying that noise was useful in their quantum simulation of some condensed matter systems, but I can't find it. I don't remember too much about it.
So
yeah.
No. I think it totally makes sense. So let's say, suppose you ask the classical device to model the noise itself. That can be very difficult. And so it could happen that, for some condensed matter problem, noise is very much part of the model. And when you try to, model them on quantum computer, you get the noise for free. And let's say you are lucky enough to, such that the noise that you want to model and noise that you get, they match a lot, there can be some metric where, we compare. Now, in that case, it might be very difficult for classical. So one has to really, think like a hacker, you have very small, there are certain, I would say, we have limited resources and, how to make use of that, you have to come up with nice hacks, which can, help you take the best out of these currently available devices. Yeah. I think that's a very nice direction to think of. Yeah. So I think Anuj made a very nice point here, and Rishi also. Yeah.